world is full of data. Every app that you use is full of data. Look, they store data about who you are, who your friends are, what they're posting. On Bank of America, they store data about how much money you have and what accounts that's in. How do these apps store data? Well, they use a database, which is a program that helps store data and provides functionality for adding, modifying, and querying that data, and doing that all fast. Databases come in many forms, but a really popular type of database is called a relational database. It stores each kind of data in a table, which is kind of like storing data in a spreadsheet. A row represents an item, and a column represents properties about that item. For example, to store data about Khan Academy users, we'd have a users table with a row for each user and columns for properties like their nickname and location. Relational databases make it particularly easy to form relationships between tables. For example, in order to store Khan Academy users and their badges, we might have a users table and a badges table, and then a user badges table to remember which users earned which badges, just by mapping user IDs to badge IDs. That's a more efficient form of storage than having to repeat everything about the user and everything about the badge in the user badges table. Most databases come with a query language to interact with the database. SQL is a language designed entirely for accessing databases and is the most popular of them. With SQL, we can create tables, change data, get back to data that we're interested in, like we want to find out which users joined in the last week or which users have a particular badge. That's what we're going to teach here, and you'll actually get to try out SQL here in the browser using SQLite, a particular implementation of it. You won't be able to write the whole app here, but when you're done learning SQL, you'll have a much better understanding of how data is stored in the apps that you use and be able to use SQL if you ever build an app. Welcome to my database. It has no data in it yet because I want to build it up with you. What sort of data should we store in our first table? Let's start with a grocery list, which you've probably used in real life. I'm pasting an example list, which has 3 delicious items and how much we want to buy of each of them. Our first bit of SQL will be the command to make the table to store this list. I'll write create table in all caps, and then the name of the table, groceries, and then parentheses and a semicolon. We see an error pop up because the SQL interpreter expects to see column names inside these parentheses. What column should we have in order to describe each item on our list? Well, first we need a name for the item, which I'll call name, and we need to follow that with a data type. We have a few options. Let's go for text. If we look on the right-hand side, we can see our new table is listed with 1 column. But we also need to specify how many of each thing to buy, like our 4 bananas. So let's add a quantity column as well, and this will always have a whole number, so let's use an integer for that data type. And now we can see that new column listed in our table. That looks pretty good if we're thinking about what data we have in this grocery list, but we're missing something that we need in databases, a unique identifier for each row. We almost always need unique IDs for each row in a database because we need a way to identify rows later when we're updating or deleting them and not be dependent on other columns because those could change. We typically specify this ID column first, so I'm moving my cursor before name. I'll call this column ID, that's standard, and then for the data type, I'll have to write this phrase, integer primary key, which signals to the database that it should treat this as the row identifier and that each row must have a unique value for this column. Okay, now we have our groceries table with 3 columns in it. It's empty though, so let's put some data in it. We'll write insert into, and then the table name, groceries, then values, and then parentheses, and here we start listing the column values in the order that we declared the columns. The first column was ID, so I'll put 1, since we haven't used that ID yet. The second column is name, so I'll write bananas, and the third column was quantity, so I'll write 4. Do you see how the schema updated on the right and now says that there's 1 row in the groceries table? So our insertion worked. Let's add the next 2 items and just doing the same thing. Insert into groceries, values, 2 peanut butter, and we'll just 1 of those because Otherwise I eat too much. And insert into groceries values in ID 3. Dark chocolate bars have to be dark. Milk chocolate is not even chocolate. And we'll get 2 of those. Okay. So it says 3 rows, but to really see that the database actually contains data, you can click the table name on the right. This will insert a select statement in your code. And don't worry too much about this now because we'll get to it in the next video. If you want, you can pause the talk through and try clicking the table name yourself to see what happens. That's it. That's all we needed to create our first table and add data to it. It's pretty cool, huh? In the next section, we'll see how to get the data back out of the table in more interesting ways. We're back with our groceries table, but we've expanded on it a bit. It now has a column for which aisle number we can find the item at the supermarket, plus we've added a few more items. Now you can really see the power of SQL in different ways that you can retrieve data from your database. And this is also where it can get a bit tricky. To start off simple, how would we retrieve all the rows from our table? To perform any query, we write select, and then which columns we're interested in, like the name, and then from, and the table name that we're selecting from. And we can see a list of the groceries on the right under that results section. But what if we want all of the column names? We can just replace name with star. And that was also the query that got inserted when you click the table name, which you might remember from the first talk through. This list is out of order though. If we went from top to bottom at the store with this list, we'd have to keep changing aisles. We'd rather have it ordered by aisle so that we can be more efficient at the store. To do that, we can just add an order by clause to our query, specifying which column we want to order by. That's better. Now we can get our ingredients faster. But to be even more efficient, my brother and I like to shop together and split the store so that I shop in half the store, he shops in the other half, and we meet at the checkout. There are 12 aisles at this grocery store, so for my list, I just want to know which items are in aisles 6 through 12. Well, anytime we want to filter results out, we can use a where clause for this and specify the column name and then what we want to compare it to. So in this case, I used a greater than operator, but there's lots of different comparison operators depending on what it is we're trying to filter by. Great. So now I know exactly what items I'm going to get. I'm going to be really efficient. And you've learned a few ways to use SQL to query. Now stay tuned to find out even more ways that you can select. We're back with our grocery list. I can see that it has 6 rows in it, but I can also see that we need to buy more than one of each item, like our bananas. So I'm not sure offhand how many items we'll end up buying total. And I'd like to know that total number so that when we're cashing out, we could just do a quick check to see if we have the right number of items in our cart. Well, to do that in SQL, we can use what's called an aggregate function. An aggregate function is useful for things like getting the maximum, minimum, sum, and average of values in our database. In this example, to get the total number of items, we'll start with select, then the name of the aggregate function we'll be using, sum, then the name of the column we want, and then from the name of the table we're selecting from. Ta-da! So we can see on the right that the sum is 15, so we should have 15 items in our cart if we got everything correctly. And notice if I go up here and change the number of bananas, because I'm going to invite my monkey friends over for a jungle party, we can see the sum increase in real time and get bigger and bigger, so we know that we're now going to need 67 items in our cart. Now we could easily try out other aggregate functions here, because sum's not the only one. So if we wanted to know what is the most that we'll be buying of any one item, then we could use max. See, 56. Those are obviously our bananas. But this information is useful for this case. Let's go back to sum. Okay. Now, what if we wanted to make sure we had the right number of items after each aisle? Well, we can do that in SQL using the group by clause. We add it to the end of a query, specifying the column name to group by aisle. Okay, so now we can see that in one aisle we have 9, another of 1, but I don't actually know which aisle we're getting each of them in. So what we can do there is just add aisle to the beginning of this select. So there you can see, okay, so we're going to get 9 items in aisle 2, 1 item in aisle 4, 56 in aisle 7, and 1 in aisle 12. Awesome. Now, how did that actually work behind the scenes? The SQL engine first did the grouping of the rows based on aisle. So first did this group by, then it summed up the quantity in each of those groups, and then finally it selected the first aisle value that it saw in each group. And, the aisle value was the same for all of them, so we got the aisles back out. But we could have also said name here, and we do see a name for each of the rows, but it's a bit misleading because for some of these aisles, there are actually multiple items in that group, but the SQL engine just picked the first item out of it. So you really shouldn't be using something different from what you're grouping by because you might not get a sensible result. So we'll say aisle, and now that's an accurate presentation of our data. Okay, so great. You've seen aggregate functions, you've seen group by, and now you can efficiently gather useful statistics on your data. Another tool for your SQL toolbox. I've spent the last few talkthroughs making a grocery list. Well, now that I've realized how much eating I do, I realize what else I should be tracking in a database. How much exercise I'm doing. So I'll start by pasting in some statements that create a table and insert a few rows of data. Let's see what I have in exercise logs. We have an ID, of course, a type, which is a string like biking or dancing, minutes for how many I spent, calories for how many I burned, and heart rate for how high it went. Now I'm inserting the data using a slightly different syntax than before. Notice how I'm specifying the column names in parentheses after the table name. When I do that, it means that I don't have to specify every column value here. I only have to specify the ones that I give in this list of column names. Now, do you see which one I didn't specify here? The missing column is ID, and that's very much on purpose. ID, here we go. The ID column is the primary key in the table, and it's set to auto increment. That means that the database will automatically fill it in for us when we tell it to, by picking an ID that's different from the other rows in the table, usually a number that's one bigger than the biggest number so far. Now, I would rather have the database figure that out than have me figure it out. So I usually like to do my inserts this way, leave out the ID, let the database do that work for me. Okay, so there we go. My database table is set up, and it looks like I've even done a bit of exercise. Go me! Let's find out where I'm burning the most calories with a simple query. I'll just modify this one. So select from exercise logs where calories greater than 50, and we'll just order by calories as well. Okay, so I've done 2 activities where I've burned more than 50 calories, and it looks like dancing burned the most. Now, I want to find out which activities I've done that have burned more than 50 calories, but also taken less than 30 minutes, because I want to exercise more efficiently in the future. It's pretty obvious from looking at the current results. There's only 2 results. It's easy to look at that. But just imagine that there are thousands of rows. Maybe this is data from thousands of users. I would need a way to filter that down in the SQL query itself. To do that, I can use the AND operator to combine those multiple conditions, like to only return the rows where calories are greater than 50 and minutes are less than 30. Haha. So now I only see one result, dancing, which means I should just spend my whole life dancing, which sounds pretty good to me. Okay, so in a similar way, I could use the OR operator to return rows that meet any of some conditions. Like, let's say rows where calories are greater than 50 or heart rate is above 100. And that helps me find the most vigorous exercises. Now we can see that dancing and biking are both good, and actually, I do like biking. It's just a bit harder. Now, you can have as many or and operators in your query as you'd like. The and operator has precedence over the or if you've got both of them in the same query, but you can always use parentheses to change the order of evaluation, just like with math expressions. Now I want you to try these out in the next challenge, and stay tuned for the next talk through where I'm going to show how to do some interesting things using this type column here. See you then. I'm back with my table of exercise logs, and I've added a few more rows. Now, if I wanted to filter these logs to just show my biking logs, I could just add where type equals biking. Simple. It's getting sunny outside, so actually what I want to find is all of the outdoor activities, not just biking. So to do that, I can use the OR operator that we just learned, checking each of the different outdoor types. So type equals hiking, or type equals tree climbing, or type equals rowing. Unfortunately, I don't yet have a mountain or a tree or a lake in my home, so all of these are outdoor activities. All right, so that worked, but there is actually a simpler way to do this query, and that's using the in operator. The in operator will check to see if a particular value is in a list of values. Let me show you. So we'll take this query and I'll paste it, and then I'm going to replace this equal sign with in, and then put a parentheses, and then I'm just going to separate each of these strings with a comma instead of that whole long or type equals blah. Ta-da! Same results like we expected, but this query is easier to read and it's a bit shorter too. We could easily also do the inverse query if we just want to see the indoor activities. We just write not in. Ha. So that's just dancing, and I'll save that for the winter time. Let's change it back to in and our outdoor activities. And I'm going to show you something a little more interesting that we can do with in. First, I'm going to need another table of doctor recommended activities. I'll paste in the SQL for that. Let's see, where do we have it? Here. So here we've created a table of doctor recommended activities, which just has a type, which matches our type from up here, and a reason, which is why the doctor recommended it. Now, what if I wanted to see all my exercise logs that correspond to doctor recommended activities? Well, first, I might want to see what are those doctor recommended activities. So select type from doctor's favorites. Okay, biking and hiking. So I could just take this query and modify it and just shorten it to biking and hiking. However, if the doctor's favorite tables changed, like there was a new row added or a row deleted, then this query would be out of date. What I want is for this query to always be up to date with what's in this table here. So what I can do is use the in operator directly with the results of a SQL query, a select query. And it's actually very simple to do. I'll replace what's in the parentheses with the query that we did before. Ta-ta! Cool. So we call this inner query a subquery. It's the query that we're doing inside the outer query. And now this query will always pull based on whatever's in the doctor's table at the time. It will stay up to date. And this is a pretty simple subquery, but it could actually get really complex. It could be as complex as any of the queries that we've learned so far. Let me show you an example. What if we only want to select the favorites that the doctor recommended for cardiovascular reasons? So we could say where reason equals, and then we could paste this whole long reason in here, and we see hiking. But what if for some reason we didn't have the period in here? Well, now we actually see nothing for that query because it's trying to do an exact match and it can't exactly match that. So there are times like this when we want to do an inexact match, and we can do that with the like operator, which is a pretty neat operator. And so to do it, we're just going to take this and I'm going to replace the equal sign with like and get rid of, because all we care about is that very important word cardiovascular. That is what we're looking for. So we say cardiovascular and we also put a percentage sign on either side, which acts as a wildcard. So this should match any rows which contains the word cardiovascular anywhere, and it did. Yay! Okay, so that's pretty cool. Whew. We covered a lot in subqueries like. Hopefully you're pumped to try them out in the next challenge, or take a break, go climb a tree, and come back. Either way, I hope you have fun with it. Let's continue with more queries of my exercise logs. Let's say that I want to see how many calories I've burned for each type of activity. We can do that with an aggregate query. Say select type and then sum calories from exercise logs, and then we're going to group by type. Now I can see each type with how many calories I've burned total for that type of exercise. Now, do you notice how the column shows up as sum calories in the results? If we want, we can actually tell SQL to give that column a new name just by writing as and then giving it the new name total calories. That can make our results easier to read, and it also has another benefit, which we'll use later. So next, I want to filter the results to only show activities where I've burned more than 150 calories total across all the times I've done that exercise. It turns out that 150 calories is the amount in 1 ounce of dark chocolate, so it seems like a good amount to shoot for. Now, my first instinct might be using where to filter. Like if I took this query here and then said where calories greater than 150, then we only see dancing and we don't see biking, which we would expect to see. The reason we only see dancing is because it filters each individual row that comes in. And dancing is the only exercise where I burned more than 150 calories in a single log. But what I want to know is which exercise type or types have I burned more than 150 calories across all of the logs for that exercise type. We actually have to use something new for that, which is the having clause. To use that, we'll remove this where, and then after the group by, we'll write having, and then total calories greater than 150. Ta-da! Now we see biking, because now it's actually looking at the total calories, and I've indeed earned more than 150 over time in my logs. So as you can see, those two queries are actually different, but they are easy to confuse. When we use having, we're applying the conditions to the grouped values, not the individual values in the individual rows. We could use any aggregate function on a grouped column that makes sense. Sum, min, max, average, whatever we want to check. Let's do another example. So if we want to see the average calories for all the exercises where we burn, let's say more than 50 average total. Oh, that's all of them. So let's up it. 100 in the middle, still doing good. 70, cool. So you can see we can play around with that query there, get different results with that having. Now let me do something a little different. Let's say we want to see all the exercise where we logged at least 2 activities for that type of exercise. For that, we're going to use a count function. So I'll select type from exercise logs, group by type, and then having count star, doesn't matter what column, so we can just do star, greater than or equal to 2. Okay, so now we can see biking, dancing, tree climbing. I've done all of those at least 2 times. Makes sense because those are my 3 favorite activities in life. Besides coding, of course. Okay, so now you've seen having. Remember that it's easy to confuse having with where when using these aggregate functions. So think through your results and make sure they make sense. And now you get to try it yourself.